Hello, everyone. Thank you very much for coming. I am Arno. I am the CTO at ThinkCell. These are the guys where you see the logo throughout the building on the videos. And I'm one of the founders. We started 22 years ago. We are still doing a PowerPoint add-in, but we are doing it in a really cool way in C++. And this is one of the things that we learned along the way to how to write better ranges. Now, well, first of all, ranges have been in C++ now since C++ 20. So who is now using ranges on a day-by-day basis? Okay, still quite a few, actually. That's interesting, because I think they're very, very practical. We've been using ranges since there were ranges in boost range. So that's 20 years ago. And we've built kind of our own library of ranges, then made it compatible with the ranges that came in C++ 20 and closely observed what they were doing, compared what we were doing, learned from each other. And yeah, this is what this talk is going to be about. Now, first of all, if there are so few people who actually are using ranges already on a day-by-day basis, this is why you want to use ranges. So say you have a vector, and you want to sort it, well, then you have to pass two iterators to the sorting function. And then when you want to throw away duplicates, you're writing vec erase did unique, vec begin, vec end, and you vec, and vec begin, vec end, and vec, and vec, and vec, and vec, and vec. And it's like, oh, I don't want to write all that stuff, right? Okay. Now, pairs of iterators, which are throughout the standard library, belong together. They are describing one object. So quite natural, just put them into one object. So then this would look like this. And this is C++ 20, ranges sort of the vector, and then vec erase, ranges unique vec, vec end. All right, I think it's clear what this thing is doing. So we are sorting it, and then we are throwing away the duplicates. Now, if you don't have a C++ 20 compiler yet, that's no excuse not to use ranges, because Eric Niebler has an implementation that you can use. And it's close enough to the standard that if later on you're switching to C++ 20, it will be pretty easy to migrate the code base to C++ 20. So I think that it would be a good start. It would be an even better start if you use our ranges, but we'll get to that later. Now, why do I think I know something about ranges? OK, now ThinkCell has a range library. Well, we actually have a library. That library is built really independently of our PowerPoint add-ins. Okay, forget PowerPoint add-ins. It's a better C++ library. We are looking at what we are using in our code, and then try to package that into useful library functions. And we really aspire to be a better standard library. We don't try to reinvent the wheel. We are building on top of the standard library. We are building on top of Boost. So whenever there is something in Boost that we find is good and useful, we use it. And everything else we build on top. Now, we have about 1 million, now probably a bit more, lines of production code that use that library. And there is a good and a bad. The good thing for us is we are ready to change production code and library code at any time. That makes the library less stable. Right? So if you want to use it and you don't want to follow all these changes, you are welcome to fork the library and just run with it. It will still be much better than if you don't have any library. So if you have a new project, or even into an existing project, it's probably good still to have it. But the ability to change the library at any given time says we have no obstacle to change the design. And throughout the code base, we kind of learn how that library ideally should look like. And there's always something you learn. There's always a better design. You can constantly tweaking it around. And then we have that large code base to try out these changes. So I think over time, doing that for 20 years, we learned a lot about how this library should look like. And this is how it looks like. OK, so that's why I think I know something about ranges, because we've been doing this process now for 20 years. Now, let's get back to our ranges, sorting and erasing. That's wrong. It's wrong, at least under certain circumstances. The problem is the sorting takes operator less. The uniquing takes operator equal. If they don't agree, this is wrong. They should agree, of course, but do you really want to rely on that in generic code? It doesn't really, it feels kind of wrong, right? So, and you don't really need, with this sorting and uniquing, the equal operator really has nothing to do with it. The less operator is good enough. So in our library, we have sort unique in place, which is the in-place version of sorting and then making it unique. There's also a non-in-place version, which is lazy, but we get to that later. And there's also, of course, also one where you can plug in the less operator. But you don't plug in the equal operator anywhere because you don't need it. OK. Now, first of all, let's talk a little bit about basics of ranges. What are ranges? First of all, the containers that we all know. So vector string list. They all own their elements. They have deep copying. When you're copying the copy elements, you copy the elements along with the object. And they have deep constness. If the object is const, you cannot mutate the elements. Now, and then there are views. Views are kind of references to containers or elements of containers. And this is essentially what we all know already from the standard library, these iterator pairs. Just an iterator pair packaged into a single object, that's a view. They reference their elements, they have shallow copying. If you copy an iterator, you don't copy any elements. So if you copy it, it's all O of 1. And it has shallow constness, right? So the const iterator, even the mutable iterator, if it's const, you can still you mutate the elements through it, kind of like through a pointer, a const pointer. And if there is a special const iterator, just like there is a pointer to const, through which you cannot mutate the elements. OK. Now, there are also more interesting views, because this is pretty boring if you just have these iterator pairs, that we use a lot. These are range adapters. They essentially take an existing range and turn it into something else. And I will talk here about the two probably most used ones, the transform and the filter. Now, let's say we have a vector of ints, and we want to find a 4 within that vector of ints, right? We would naturally use ranges find and give the vector and the elements we are looking for. And then we get an iterator back that points at what we found. If that integer here that we are looking for is not it's straight in a vector, but it's embedded in some substructure, like down there, structure A has this int ID and then some data attached to it as well. And then you have a vector of these things, right? And they also have these integers, 1 to 4. But if we now want to find, the find looks very different. We can't reuse the find that we used up there. We have to write it with a find if, because we need to access the ID here. And so that means these two things are quite similar in semantics. They can do similar things, but they look very different in syntax, which is not nice. And really the problem here is that we munch two things together. One is the projection onto the ID, and the other thing is the finding of the 4. These are two different aspects, really, that we should be able to pull apart. That's why there is a transform adapter, where you first basically take the vector of a's, and you transform it into a vector of ints, and you do that lazily. So you apply this transformation function lazily while you are iterating. You get an iterator, and every time you dereference the iterator, it will actually call the projection function and gives you back that projection. And now you can use the regular range find to find your 4 in that transformed version of your vector. Now, one thing to point out here is what's the iterator pointing to? Well, the iterator is pointing, in this case, to numbers, ints, right? Because we projected the whole thing onto ints. It's natural to say, well, but I want the a's. I'm finding the 4, and now I want to know what's associated with that 4, so I have to go back to the base. And you can do that by just calling .base. And that basically takes the iterator from the transform, unwraps it, and gives you the raw iterator back, which is then pointing to the a's. Not bad. OK. Now, here is a possible implementation of this transform. And one way to do it is that you're writing an iterator that carries around this projection function. And every time you invoke the operator star, it will actually invoke the projection function and return the result. And there's also the base, which actually just returns the iterator that is encapsulated, that is aggregated by this wrapping iterator. Take note that we are carrying around this function in every iterator. Maybe not so good. We'll see. Here's the other one. I said transform and filter. Here's the filter. Let's say we again have our vector of a's, and we want the ones that have id equals 4. So we want to just have the elements with id equals 4. Again, this is lazy, so this filtering actually only happens when you start iterating. Creating the filter range is essentially O of 1. It's very cheap. And only when you start iterating, it will then basically skip the elements which are not passing the filter. Here is a possible implementation. Now you again have an iterator that is basically the iterator of your filter. And it has a functor and 2 iterators. One is the base iterator, where we are currently at, with which we skip the elements. But the problem with the skipping, and that's clear from the operator increment down there, with the skipping, the problem is, well, we may fall off the end. We need to know when to stop because we can't dereference the end iterator. So we need to remember the end iterator, so when we are incrementing, we're not falling off the end. We don't need to remember the begin because dereferencing begin is illegal. So you can't do that, but you can increment the one before end, so you need to remember end so that you don't fall off the end. Okay, so we have a functor and 2 iterators inside each iterator. Now, how does this iterator look like? You have a filter of a filter of a filter. You're saying, oh, well, why don't you just have a single filter? And that's pretty stupid, right? Well, I mean, imagine one of these functions one function is returning a filter. And that is consumed by another function that adds another filter, and that's consumed by another function that adds another filter. So these filters don't necessarily know of each other. And they shouldn't have to, right? So these things may come about just because you structure your program in that way. And it's fine to structure. It should be fine to structure your program in that way. You don't want to optimize the number of filter adapters that you are using. That's the iterator. It gets an awfully big iterator. The iterator grows essentially exponentially with the number of levels of transforms or filters you put around, which is not good. And boost range did this. Not good. Now, we have to keep our iterators small because we'll run small loops, like tight loops with them, and we'll pass them around by copy. And all that means that we don't want to make them huge because then they get very expensive to copy. So here's the idea. The adapter object, so the object, not the iterator, but the object that is associated with the filter, it will actually carry around the end iterator and the functor. And then the iterator will be very simple. It will simply be the base iterator with which we skip. So where are we in our original sequence? And a pointer to that object, that filter object. That is C++20, state of the art. And that's the reason that C++20 iterators cannot outlive their range unless they are borrowed ranges. So for filter and for transform, in the standard library, they said you need to keep your range alive because we want to store stuff in it. In particular, for the filter iterator, we want to store the end iterator. So let's see how well they did. First of all, consequence of this decision that the iterators cannot outlive their range, there is some danger. So if you call ranges find on this transform, it will actually not compile with the standard library. Because they are afraid that if you call views transform and I think I made a mistake. Yes. So I made a mistake because v, imagine v is an R value. This guy. That's an R value. Okay? So you generated a vector and then you immediately want to transform it. No, disregard. Disregard. Correct as written. Correct as written. the thing is that the range is fine still takes a PR value. And so because we are generating this transform, we are wrapping the vector into the transform, that's a PR value. Now we are pulling an iterator out of the PR value. Now the standard is afraid that that PR value will go out of scope. And the iterator relies on this transform to be alive, to stay valid. So they are afraid if you're giving me an R value and you say, give me an iterator back to this R value, what happens if that R value goes out of scope? That's what they're worried about. In this case, there's nothing to worry about because we call .base on it. So it's fine because the iterator that is returned by .base is pointing to the vector v, which is not a PR value. So this is okay. It will still not compile because they're afraid. So you have to wrap essentially this thing around, you have a little utility as L value that essentially it turns the R value into an L value reference, pure cast, purely to satisfy the compiler and say, it's fine, I know what I'm doing, all good, okay? Silences the error. Okay. Now, let's do the same exercise that we did before with the wrapping of filter, 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 filter. This is what you get. It's still linear. So you have a back pointer to the range, and you have the iterator, but the base iterator still has to hold a back pointer to the range, and an iterator, and a back pointer to the range, and an iterator, and so on and so on. So it's still, you get a linear growth of the iterator size, which the standard said, that's fine, can't help it, whatever. We said, nah, that's not good, that's not nice. You want to be able to stack these things like crazy, and we shouldn't pay anything for it. So how do we do this? The key here is that you need something more abstract or a different abstraction than an iterator. An iterator is not quite good enough. We call this thing an index. An index is just like an iterator, with the exception that for all its operations, it needs the underlying range. So you need to give it the range and the index. And then it can do things like increment, decrement, dereference, and so on. But always you need to supply the range. Okay? And that would essentially be the interface. You have an index range, and then you have functions on it, member functions, begin index, end index, increment index, and they begin index, end index, return the index, and increment, decrement, or dereference. They always take the index as an input, and they are member functions of the range, so they have the range and the index. Okay. Now, of course, if I tell you this, and then tell you, well, now you have to rewrite all your code to use indices instead of iterators, that's going to be a no-go. We don't want that. We still want to use iterators probably in our code, because that's what we're used to. So, and arguably, it's also simpler to do that. Okay, but still, that's not so bad, because it's pretty easy to fix this compatibility between indices and iterators. So if we have an iterator and we want an index, that's trivial, because we can just use the iterator as the index. If we then basically get a range supplied to it for free, then we just disregard that. We just execute whatever we have to execute using the iterator. So with a bit of glue, we can just say, well, use the iterator. If you only have an iterator, if you don't have an index, forget about it. We just use your iterator as the index. And this is what we did for your normal ranges that there are. So we don't want to reinvent the vector and the string and the list. We just can use it because we can use their iterators as the index. Now, if you only have an index, but you want an iterator, that's also not very difficult, because you can simply build an iterator that, again, just holds a pointer to the range and the index. And then it can implement all its operations in terms of these two pieces of information that it has. So here, operator increment is calling range increment index with the index. And it has both of these things, the range and the index. So it's trivial. You can easily now turn something that only supplies indices into iterators with a bit of glue code. Now, let's see how now the filter looks like. The filter would contain the function and a reference to the base range that it actually is filtering. And the increment index is then relatively easy to implement. You can just say, okay, my index is the same as the base index. And that's important, because as you imagine, when we have the stack, then we can now stack gazillions of these things. The index is always going to be the very base, the index of the very base range. And it will always be, in this case, if we filter vectors, it's going to be the vector iterator. So you essentially, any one of inside the stack needs to just remember, okay, my position is a position inside the vector. That's it. Doesn't matter how many stacks are in between. And when you want to increment, you can just ask kindly your base to increment this index. It's like, here's my index. Please increment that index. And it will apply its own predicates and filtering and whatever there is all the way back down to the base, and then return you or do this for you for your index, mutate your index, and say this is my index that I changed for you. And so you don't need any more information about what's there in between in this stack. It will just automatically work. Same with the end. You can just ask your base for the end. The base can decide, are you at the end of this list? And if you have a stack of filters, then all these end checks will just go back down to the base, and it'll just at the end will just be the vector end. So it will all fall apart into very, very simple operation. And dereference the same. So it's all quite simple. You just pass everything down the stack. And if you are holding the base by reference, which is done here, then this may involve some indirection. There is also, in our library, if you pass an R value, and you can have similar function actually in the standard library as well, if you're passing an R value, it will actually hold, the adapter will hold the base range by value. So in this case, it will really all be inlined. It will all be the single object. Okay. Yes, and the iterators all have 2 pointers. So pointer to the base range, and in this case, the vector iterator, also a pointer. And you can stack as much as you want. Okay, on to the next idea. When you are calling std algorithms, then you quite often get an end back to say, oh, I didn't find anything. Right? Or I didn't, something, it's singleton. I don't have an answer for you, here's the end iterator. And so the typical thing is, yeah, I'm finding something, and then either assert it's not end. Or if it's not end, do something. Which is not nice, because you have to, the range that you are having there, that you are checking, that you are passing into the algorithm, you need again to do the end check. So you're always mentioning every range twice, which then you cannot inline it, you need to assign a variable name, and so on. Not ideal. So here's an idea of how to do this in a more compact way. Let's say we have algorithms, and we can basically tell them what you want to have returned in case of singleton result. So, for example, for find, you are running through the whole sequence, and if you found what you're looking for, then you pack this up as the result. And if you don't find what you are looking for, then you pack a singleton. You say essentially generate the default answer, the fallback answer. And now you can define what that fallback answer should be in the caller. So we have these little structs that essentially traits that tell the function, well, what to do when you come into one case, when you go into one case or the other. And when you're now calling find, you can say, well, either give me the element or give me end, if that's what you want. Okay? But instead, you could also say, I only want the element. This end case is not a case that I'm expecting here. I don't want that. And that's very nice to write that into your code, because it's documenting it. You can tell by reading the code, this guy is not expecting the end case. It's no longer an assert that you have to write in the second line beneath it. You can just directly state what you are expecting from that function call. We also have one version that packs up the iterator into a wrapper, an element type, which is nullable. So that you now have a nullable type being returned when the singleton case arises. So when you do a find, you can just simply find if auto it find, and then just you go into your branch of doing something when you found it. There's more you can do. You can do things like return me the prefix before the things that you found. You return everything before the element. That's a subrange. Return everything afterwards. That's probably the. Include the element that you found, don't include the element that you found. So there are various things that you can plug in there that makes it a whole lot more expressive to write what you want. That's a different talk. There is a different interpretation of iterators depending on whether you found an element, where the iterator is really pointing at an element, or the iterator is pointing at a boundary, really like basically slicing the range you passed in two, like lower bound, upper bound. It really gives you two parts. And there you can do similar things, give me the subrange before, subrange after, and so on. So there are different traits to use for different algorithms. Okay, next to another idea. Say you have a visitor pattern, right? You traverse widgets here. And you have a sink that you pass in these widgets. So if you have something, then you traverse these widgets recursively, and then you have some widgets that are always there, and then there's another window, and you traverse widgets. You essentially go through this tree of widgets and enumerate them all, right? It's a little bit like a range, right? Now, it's a visitor pattern, but it's a list of things. So why not make it a range? Well, we don't have an iterator, okay? Is that a big problem? How big of a problem is that really? Let's try to make that a range so we can use it as a range. We can use the same algorithms that we use for ranges. Now, for example, write something like this. I want to know, did I hit any widget? Well, if it's when I traverse my widgets, that's my range there, auto sync, traverse widgets. Then in any one of that has a mouse hit, then my mouse got hit. Or I hit something with a mouse. Should be able to write this. I think it's nice. It's very practical in our code. Now, what's really happening here? Typically, the typical C++ iterators that we know do what's called external iteration. External iteration means that the consumer of data calls the producer if it wants more data. And the producer returns that data. Consumer consumes that somehow and does something with it. Whenever it wants more data, it again calls the producer. So the consumer is at the bottom of the stack, and the producer is at the top of the stack. Now, that has advantages for the consumer and disadvantages for the producer. The consumer, it's always nice to be at the bottom of the stack, because if you're at the bottom of the stack, you have a contiguous code path for the whole range. So you are never your code flow is never interrupted for the whole range. That makes this consumer much easier to write. It also has better performance because you don't have to restore the state of your consumer when it's being called. It's never being called. You are always in the same piece of code, and your instruction pointer basically encodes the state of that consumer. So if the code path of your consumer is very complicated, that's a nice thing to have. The producer is at the top of the stack, and being at the top of the stack is not as good because you only have a contiguous code path for each item. So every item is again entering the code at this operator star. And you have to essentially, in this operator star, restore somehow, where am I in my sequence? What do I have to do? I cannot write this as a contiguous code path, which in case of that recursive iteration that we just saw with the widgets is difficult because we need to basically know where am I now in my tree, and that tree is very easy to write if you just write one function that calls other functions, just make recursive function calls. But if you have to traverse that with iterators, it's a whole lot more complicated. Makes it harder to write. Also has worse performance because you have the single entry point. So no matter how you do it, you still have to, when operator star comes, you have to say, well, where am I? And where do I have to continue? Also, between elements, you only can allocate a fixed amount of memory, because you essentially only have whatever you are storing in your iterator is your state. You cannot just say, well, I dynamically just get more memory from somewhere that is from the stack, because that stack will be gone the next time operator star is being called, obviously. So then you have to go to the heap, which is less efficient. Now, what you can do, and it's kind of funny that I think that the C++ library doesn't support that, is you can turn these things around. You can just say the producer sitting at the bottom of the stack now has all the advantages of being at the bottom of the stack, and the consumer is at the top of the stack. So this is essentially the case where these for each something, when you have a for each something call, that's essentially turning this around, because the for each function call will produce these items and will just pass them into you. Or visitor can also call it the visitor pattern. Really, the ultimate turn this around function is std for each. Std for each is essentially says, call me back with all your elements. Well, in this case, you essentially relinquished your bottom of the stack position and say, well, I'm actually happy with top of stack. I'm happy with being called for each element. And that situation is very, very common. We always write for eaches all the time. And in all of these situations, we are happy with being at the top of the stack. So the producer, we could give the luxury of being at the bottom of the stack to the producer, and maybe you can do something with it. Let's see. First of all, can both the consumer and the producer be at the bottom of the stack? That'd be, oh, everything is fine, right? We both have the luxury of being at the bottom of the stack. Yes, you can with C++ coroutines. But C++ coroutines have their own problems. First of all, you can write this, which actually is std generator. It's supported. You can write that code. Except every function that this coroutine calls has to be a coroutine. So it means you have to coroutine your whole call tree. Otherwise, it won't work, which is annoying. And that's one of my big gripes with coroutines, that you essentially have to coroutiniFy your whole code base in order to use coroutines. In particular, imagine that this traverse widgets, if it's a custom function traverse widgets, that's possible. But what if I want to use algorithms here? What do I want to use generic functions? I would have to have them in two versions, one basically being coroutine for coroutines and one for non-coroutines. Kind of weird, strange. So you have to coroutiniFy your call stack. Now, and it's still a bit expensive because the re-entry point to the coroutine is some sort of dynamic jump. You have to remember where you are in a coroutine. You have to get back to it. You have to save and restore some registers. So you have to really have the compiler has a tough time probably to find out which registers do I have to store and save and restore at the point of switching between the coroutines. If the compiler optimizer is really, really, really good, maybe you can do that, but it's by no means assured. So same with inlining, right? So it's much easier to inline if the compiler knows exactly which function it needs to inline, while that decision is by necessity dynamic if you have coroutines. So the compiler has a lot more work to do. The deep coroutinification you can also avoid, but then you're really going to stack full coroutines, which the standard doesn't have. And it really means you have two stacks, you have to switch between them, you have to implement them as operating system fibers. It's going to be very expensive and nothing that you want to use for a tight loop that you typically have in range code, where you have a very tight for each loop that has to be very efficient. So, and it turns out the internal iteration is often good enough. You can write quite a few algorithms with internal iteration. You can't write find or binary search because we don't have iterators, and they output iterators. But many others you can. For each, that's basically the mother of all internal iterations, of course. But accumulate all of, any of, none of works. We can also have adapters. We can have a filter. We can have a transform for internal iteration. I mean, if you pass me an element, I can transform that element and pass it on. No problem, right? So, these algorithms in the standard ThinkCell library all support internal iteration. Now that's how the any-of implementation, for example, looks like, right? So you're saying my result is false, and then you iterate, and then you see, well, anyone true, and if yes, then it's true, and if not, it's false. And yes, there's an any-of actually in our library that doesn't take a predicate, just does a Boolean evaluation, which also turns out to be practical. Now, of course, here's a problem. The problem is any-of is lazy. So we should stop, really, when true is encountered. When you see true, you say, oh, it's true. OK, stop. Don't iterate further. So we have that as well. The first idea was, we use an exception to bail out. Well, of course, exceptions are way too slow. Don't want that in tight loops. And don't want to do this all the time. Now, the other idea is, well, we just define a specific enum, break or continue, and the TC for each implementation can basically decide when looking at one of these at the sink, its sink, does it return something else but break or continue? Then it's normal. I don't have to check whether it's break or continue. I can just carry on. Or if this guy returns break or continue, you decide that at compile time, then if it returns break, I have to stop. So you kind of elide the break check when you don't return break or continue. So you don't lose anything performance-wise with that check. Now, how is that useful now? This internal iteration. What does that buy us? Here's an example, quite frequent probably. You have concat, which is just concatenating two ranges, turning it into one. Now, if you run that together with a for each of concat, right, with indices, that would be quite complicated. So you have a concat range, and it basically has to carry around a variant of two indices. You need to know in which of the subranges, you have two subranges, you need to know where you are. You do need to say, I'm here or I'm there. Now, that means that every time you increment, and you don't remember anything, you get your increment, it's like, okay, where am I? Am I here? Okay, increment. Am I there? Okay, increment that guy. Different code for either case. So I can't put this all in one bag. I just have to decide. I have to make a branch of what you need to do if you increment. Now, dereferencing. No, oh, surprise, I first incremented, now I dereference. Again, I have to branch. I have to decide, okay, I'm either here or I'm there. And again, do the right thing for each of these ranges. How do we avoid this? Well, it's easy. For generators, for internal iteration, it's so simple. We just write two for eaches. We just iterate over one. When we're done with that, we iterate over the other. We don't lose any performance. Much better, much easier. No branches at all. All good. And that doesn't mean we don't have the iterators. The concat will support iterators, and it will support internal iteration. And if the guy who's doing stuff gets by with internal iteration, it just uses the internal iteration interface. And then it gets the internal iteration performance, and everyone's happy. Now, here's what we can do now with this internal iteration. Another thing. Std format, also C++20 new. Surprisingly, although they introduced both in the same version of C++, std format does not use ranges. They had ranges, but they didn't introduce ranges because they designed std format. One guy designed std format, and the other guy designed ranges. And they never really talked to each other much. So we have now std format, and we have ranges. And they don't really fit together very well. So here's how they fit together. Now, std format is actually writing to output iterators. And output iterators are, in a way, already internal iteration, because you are essentially passing the things that you are producing to this output iterator one by one. So that's internal iteration. And it's much easier. When you are turning a number, for example, into a string, you have to hold state. So it's quite nice if you can write this with internal iteration, if you don't need external iteration. And typically appending to a string doesn't hold much state. It can just take the characters one by one. So it's quite natural to use internal iteration. And now with the generators, we can actually do this with internal iteration. So let's say you're writing a string like this. You won number of $F, okay? And this sdec is really just a generator that generates the number. Think of it as a range. That's the string that is written by this f and with two digits or two decimal digits. And in ThinkCell, you actually are required to pass a decimal separator as well, which I left out here. Required because you want to know when you're doing all international code, right? And we don't need internationalization, so you need to specify what kind of decimal separator you want. Note that it's not like IOStream. IOStream allowed you to put that double straight into the string, which is kind of confusing because what's happening when you're putting a number into a string? What does that mean? Well, it meant something. It's based on the state of that stream. But that made that stream quite cumbersome. A lot of virtual functions, a lot of state that was carried around. How many decimal places do you want? Does that decimal place, oh, I forgot to reset the number of decimal digits, and now I'm getting an unexpected output. No one loves IO streams. So that's why that's not a good idea. It's better to say, here, this is essentially turning my whatever I have, whether it's a number or whatever, it doesn't matter, into a string. And this is the range that is essentially that I'm giving you, and please add that to my string. Now, this is also easily extensible. I mean, there's in std format, there are also customization points, and you have to write them in a certain way, and it's all complicated. No, you don't need that. You only need a function that returns a range. And then you just naturally extended the stuff that you want to format. Right? Like here, there's dollars is okay. You put a $sign in front of it. Okay, that's my formatting function for dollars. 2 decimal digits and a $sign in front of it. And I just write this into a function, and now I can use it wherever I use strings. Right? Easy. And this is how we actually do a lot of string formatting. We have an HTTP server for our website, and that's how we generate the strings that are coming out of it. It's whole database like queries and turning the database query blah 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 into a string, and you want to format it as a table and blah blah blah, blah big stuff. You can all write this basically in one expression. Turn your database query into strings. There's how you format strings that have placeholders, right? So you can have there's a TC placeholders that allows you to put Python style placeholders into the string, or std format style, whatever you want, and it will go by order. Okay, you can also name them. Here's the named version of this thing. So you can say, well, it's amount and date, and then you can give it named arguments that replace the amount and date if that's what you prefer. And I think it's right that when you translate this, when you internationalize this string, what will get passed to the international, usually use some sort of agency, or you build yourself a front end for DeepL. But what you will pass to that translator is really just the format string. It will not contain the number of decimal digits. In std format it would. But I don't think that's right, because typically you determine your number of decimal digits in a more formal way. You either know your data, or you look it up. You say, well, this is yen, I don't have any decimal digits, or this is dollars and I have 2 decimal digits. Whatever you have to find out how you want to format that number, it really does not depend much on the translation of the actual language. So here we designed this so you can pass this to the translator. Even if the translator messes up entirely, there is no danger of bad things happening. And the worst thing that can happen is he or she misspelled the placeholders, and then you won't get a proper output. But there's no no danger of anything else happening, like numbers being printed in funky ways and stuff like that. Yeah, so here with the date, I actually, I have this other formatter in there, the ISO 8601 formatter, which turns any date into an ISO 8601 string. So it's easy. It's easy to extend these things. Okay, and the name things are good for, of course, for reordering, right? In different languages, it may be ordered in different ways. So in this case, the translator has the freedom to do that. Now we want to form it into containers. Now, of course, the std string gives us the empty construction, right? That kind of, it's no parameters means empty. One parameter means use that parameter for the content of that string. Okay, makes sense. And then there are two, of course, okay, so that is what we need to add, right? We should be able to add the construction from one range. And that, of course, doesn't work, but we somehow have to put in glue that it will make it work. That you can basically create a string out of any range. When we have a range, you want to make a string out of it. You should be able to write this. Unfortunately, you can't, but we'll pour some glue onto it so that you can. The last one is a concatenation. Now, if I look at this first one, empty construction takes no parameter. One parameter means take that parameter as your content. Multiple parameters means that shouldn't that mean that that's the content of the string? If I'm passing 3 parameters to the string, right? Doesn't that mean that the concatenated version of these 3 parameters should be the string? I would think so. But no. They're very important 2 parameter constructors of strings. Let's look at them. Look at them. There's n ranges. Okay, this is what we want, right? Here, this is what I want. Multiple ranges, all concatenated is a string. This is what I wanted. We have very important 2 parameter constructors of the string. Okay? I'm sure that if you look at them, you immediately know what they mean. Look at them. Everyone knows what they mean? Yeah? I didn't. Okay, that's UB because A is considered a buffer. Okay, so you try to put a length of 3, the buffer of a length of 3 in the buffer A, but that's UB because A is only too long. A in the multiplier. Okay. This one, as you all know, probably it adds 65 times Control-C into the string. Okay, this is exactly what I want in this case. And that adds 3 times the A. So good luck. Okay, let's deprecate these things, right? We don't want them. We can write it easily like this, right? Make a range that repeats A 3 times. It's a lazy range. We have one for it. Just add this to the string. It's just like another range. We don't need constructors for all this stuff. We just describe the range, construct our string. Now, of course, we can't have this because we cannot change around std string. But ThinkCell throughout the library uses kind of to simulate or remove constructors. It uses explicit cast. You can name it whatever you want, but point is that this is a glue function that essentially simulates the constructor. This is our constructor, this function. That means it by default can pass to whatever constructor the default constructor. But if you want to remove things or add constructors, you can do it by customizing explicit cast. You have a customization point to change around constructors, which is very useful. So now this works in the standard in our library, right? So this explicit casted string of these multiple arguments now constructs a std string. Here's a similar thing. The cont mplaceback is again a wrapper for mplaceback pushback, but that uses tc explicit cast if it needs to. So if you find something where you want explicit cast, it will use explicit cast. So again, to keep this illusion alive that explicit cast is really the constructor. So this is like basically throughout the library we use explicit cast. We can also append, right? So you can do the concat and either we append with concat or we just have multiple arguments and they're all being concatenated automatically. Now, let's see how we can speed up the formatting into containers. The idea would be we determine the string length, then we can allocate, for the whole string, we can allocate the object, allocate memory, and then we can fill in the characters. Okay, so maybe that's something that we can reap as a side benefit from having everything as a range. So we could write it this way, where explicit cast essentially just takes iterators, begin and end, and then constructs the container. The problem is, for non-random access ranges, the string constructor runs twice over the range. The standard library assumed that iterating over a range is cheap. It is no longer in a range world. In a range world, it's expensive to iterate over a range. But they assumed it's cheap. So the standard says, we are only allocating once when we construct a std string. That's important. We don't want to avoid memory allocations. We don't care about the iteration. So no matter how complicated your range is, the std string constructor, when constructing from a non-random access range, will iterate twice over the range, which may be very expensive. So the idea here is give the poor range. So first of all, avoid iterating twice. We will always only iterate once. And if we need to, we will reallocate the string multiple times. But if you want it to be fast, then just give a size function to the range so that the size can be determined upfront, and then only a single allocation happens. That's the idea. So determine the size of the whole thing at once, upfront, single allocation, and then iterate over it once. Now, so we have an explicit cast where the range has a size and is not a random access, and then you can do the reserve with std size, and then iterate. And for list, for example, not random access, that's fine. So otherwise, you would have to iterate. You would have to still reallocate multiple times. Here you don't have to, because list, for example, would have a size. There's also append. Watch out, there's a cont reserve. Cont reserve is evil. Cont reserve is evil because cont reserve doesn't take into account what you reserved before. If you are adding something repeatedly, that is only one character, add, it will reallocate every single time. Horrendous. Okay, there's cont reserve in our library. Doesn't do that. Okay. It at least doubles the size of the allocated memory or something like that. So let's get rid of this. So better reserve. And then what about the generator ranges? Now, we have an appender customization point where you can add, for each container, it will get the appender. It's now a property of the container to get an appender. And that appender, by default, just does an emplace back, right? This also works. That's a sink for generators. But you can also have a customization point chunk, which takes the whole range at once. And here again, you have the possibility to query that whole range for the size. So even for the generator, you could write a generator that outputs these things one by one, internal iteration, but still has a size member that can tell upfront, that's my size, and then the container, we pre-allocate that size upfront, and then you're faster. For files, that's also useful because chunks of continuous memory you can write with one go into a file. That's efficient. Now we measured how fast that is. And it turns out, I'll skip over the details, if you do it iterator-based, we are wasting 50% more time over a handwritten loop. But if you use internal iteration, we are at 15%. So it's quite efficient. You write very high-level code, and still you get a lot of performance out of it. There is another opportunity for optimization, which I skip over, so we have a bit of time for questions, where you can when you add things to a string one by one, it does the end check every single time. Although you know I pre-allocated, the system doesn't know that. And you can optimize for that. We haven't done this yet. But you could, with that same interface, you could say, I am essentially having an appender which is not checking for end. Because I asked before the size, and now I can write that whole memory in one go without the end check. And that actually, that's the one. So it's basically just put it to the end, increment the end. Just do that in one go. That saves 20% in Visual C++, again, when just filling a string. So it requires your own basic string implementation, which we don't have yet. All right, you can do more. You can, for example, if you don't have a size, but you know a minimum size, at least then you could say, well, I know roughly how to allocate. Not exactly, but I know it's at least 100, so I can already allocate 100. And I don't start with 1, 2, 4, 8, and so on. Okay. The custom file appender can be even more optimized if you had your own file buffer. Because file buffer, they get written out with a cluster size. So you could really just fill the cluster. If you know I'm, again, 250 bytes, I know there's no end at 250 bytes. You can just write 250 bytes, no end check. Because I asked you before, how big are you? You want 250 bytes, okay, just write 250 bytes. Now I have, I don't know, so many bytes left. I know how long I can write. It's like, oh, stop here. Now we have a range that may run into end. So run into end, stop right there, and then write out my cluster, get a new buffer for a new cluster, and keep writing. Can all be done. Conclusion is, ranges are very useful. We had index-based ranges and generators. They improve performance over C++20 ranges. And there's also plenty of opportunity to unify ranges with text formatting, which is very useful for us. Now that we have all this range stuff, and this is the URL to our library, a lot of useful stuff in it. Again, if in your project, looking for a library, use that library. If you just want to copy it, fork it, run with it, without bothering about the changes, you're still going to be ahead, I think. I think it's a very good library. I hate the range-based for loop. Don't use the range-based for loop, because it makes people write things like this instead of this. Thank you very much. Questions? Questions? No questions?
Hi. Did you have the chance to look at the Flux library from Tristan Brindle? It's also based on, he calls it cursors, but it's basically the same as you did with the index. Just remembering like the index and then.
No, I haven't seen that library. There's also another piping library out there, I know, which is very similar to the generator library. Is this library compatible with regular iterators?
Yes, some adapters.
Okay, So yeah, maybe I took it. Maybe you can talk about it afterwards. It would be interesting. Yeah.
Okay.
Mm-hmm.
Hi, thanks for the talk. I especially like the formatting. It looks much nicer. In the beginning, you said that the old boost range iterators are kind of very fat because they contain everything in the iterator. Do you have performance data on how much that actually matters? Or are you aware of any other like comparisons between boost ranges versus range v3 versus ThinkCell ranges versus the new standard?
No, but I do know that I brought up this topic on the mailing list when they designed the C++ ranges. And at least they all said, oh shit. And that basically was then I think it was the kickoff for saying iterators have to keep the ranges alive. We need to require this because that's non-obvious. I think the first iterations didn't require this. So at least, I don't know. I mean, I guess with exponential growth, I mean, you can always make it bad. It's just how many you have to put together. So I think exponential growth is always so bad that you have to do something about it. I mean, if then you add 3 more, and it's all going to explode. So yeah.
All right, thanks.
Hi. What I'm missing in current implementation of C++ ranges is parallel processing. When I move from iterator code to new ranges, is it possible to add such, for example, sort, you can add std_par, and you have parallel processing. Is it possible to add it to your?
Probably not as much. I mean, the ranges are, or the way that they parallelize ranges does rely on the fact that you can chop these things up into pieces and then operate on pieces. Really, the ranges, the generators, I think, are most useful in this very frequent case where you have small loops, tight loops, very low-level loops, essentially, where this inlining is just very important. If you're doing a lot per iterator dereference, or if there are big operations, then that overhead for dereferencing doesn't factor so much anymore. So I think for parallelization, then yeah, you would probably need to do it manually. But for these very frequent tight loops where you don't really think about it, how many for eaches do you have in the program? It's just many, many, many. There, it does something for you.
So we have 2 questions from the internet. One question is, does your library have a shallow constantness problem as C++ ranges? Also views...
I didn't quite understand. Go ahead.
Sorry?
Say again the first question.
No, this is one question. Does your library have a shallow constantness problem as C++ ranges? Also, some views cannot be passed to a function that accepts values as const reference, like drop, in C++ ranges. Does your library have the same problem?
Do we have shallow constantness problem? When designing this library, I had a big headache because of exactly this problem. Is there a way to ensure that if you have a range const reference passed to a function, that you're guaranteed there is no mutating happening? I think per se this is I wouldn't say impossible problem to solve, but I think it's a very hard problem to solve, because a transform can always turn whatever item you have into, say, a mutable pointer. And per se, you don't know what you're mutating there. It could be something that's within the range. It could be something well outside the range. So what would be really useful in this particular case would be that there is just no mutating ever possible, so that it's a real pure function that you're calling it. Your iteration is really pure function. There's no side effects. And I think this is very hard to ensure with the compiler, because you could pass out a proxy object, which then turns it could be passed out const, and you call it, and it gives you something mutating out of it. So it's something that I don't think, thinking about this, I don't think it's a range problem, this const problem. I think it is a language problem. It goes much deeper than the language. If you have than ranges. If you have a function that is marked const reference and you call this method on a class, then this class is still able to return you a pointer through which you can mutate the world, essentially. And I think that's wrong. I think the language should have something that ensures that something is a pure function, has no side effects whatsoever. But I think just C++ does not have that. And I believe this has not so much to do with ranges. In particular, if you are looking at transform, because transform is effectively calling a general function. And guaranteeing anything through that general function is going to be impossible. So I gave up on it. We are still having the convention that if you don't want to mutate the range, you take it by constref. But that doesn't guarantee that you cannot mutate anything through that range. It would be nice if we could, but I think it's very hard, and I think it's maybe even beyond the scope of ranges. There was another question?
Yes. So can the library use as open source?
Yeah, it's a boost license. You can use it as you wish.